Welcome to Indirect Measurement. Now that you understand how to use triangle similarity theorems or shortcuts, you can use those to help you solve for missing measures in similar triangles. We're going to start off by watching a short video with an example on how to do this.
Welcome to an example of indirect measurement using similar triangles. An application of similar triangles is to be able to determine lengths indirectly. For example, let's say on a sunny day, you're trying to determine the height of this tree. One of the reasons it'd need to be a sunny day is that on a sunny day, this tree would project a shadow on the ground. So instead of trying to determine the height of this tree by climbing to the top and then somehow trying to drop a tape measure from the top to the bottom, we could use the height and the shadow of a much smaller object to determine the height of the tree. This is what I mean by that. Let's say this is a yardstick, and a yardstick is 3 feet long. This 3-foot long yardstick will project a shadow on the ground as well. And let's say we measured the length of the shadow of the yardstick to be 5 feet long. So what we have here is actually a right triangle that would look something like this. And there's actually a much larger triangle formed using the tree and the shadow of the tree in the same way we formed this small red triangle. There's a triangle formed by the tree and the shadow of the tree. And this large blue triangle would be similar to the small red triangle by angle similarity. They share this angle here, and they also both contain a 9-degree angle, which would also be congruent. Which means in order to determine the height of this tree, we would just need to measure the shadow of the tree along the earth, which is obviously a lot easier to do than climbing the tree. So if we measure the length of the shadow to be, let's say, 25 feet, this is enough information to allow us to determine the height of the tree without ever leaving the ground. Let's go ahead and take a look at a cleaner diagram of this information. Again, x would be the height of the tree. This longer side here is 25 feet, the length of the shadow of the tree. And here we have the yardstick, and here we have the shadow of the yardstick. And again, we know we have two similar triangles by angle similarity. So let's go ahead and set up our proportion. X to 3 must equal 25 to 5. So to solve for x, we'll cross multiply. 5 times x, or 5x, must equal 3 times 25, which is 75. Divide both sides by 5. And 75 divided by 5 is equal to 15. So x equals 15, which gives us the height of this tree without ever having to leave the ground. So that is pretty amazing that we can use the properties of similar triangles to determine lengths indirectly.
Now that you've seen an example using indirect measurement, let's go ahead and try one that you do on your own. So here we have Stonehenge, and say you wanted to find the height of one of these stones. Well, here's our sun, and our sun causes the stone to again cast a shadow, and we'll say that this shadow is 6.6 meters. Well, we can measure that with a tape measure, the length of the shadow, and then we can take a yardstick and place it anywhere. And the yardstick then is obviously 1 meter, and we can measure the length of that shadow as well. And let's just say the length of the shadow was 1.2 meters. So now we have enough information in order to help us solve this problem. And remember that these two triangles are going to be similar by angle, because number one, they're both right triangles, so there's one angle. And then the angle at the top, due to the sun, is going to be the same. As long as we measure quickly before time passes and the sun changes the angle, then these angles are going to be the same and these lengths are going to be proportional. So our triangles are similar due to AA. Go ahead and pause the video and see if you can solve for x, the height of this stone. Okay, you should have set up proportional ratios. We can say that this small triangle, the length of the shadow, is going to be proportional to the larger triangle's shadow. So that's our ratio. And then we can set up another ratio with the heights. So we have a 1 meter stick, and we're trying to determine the height of this stone. Once we have our proportions, we can just cross multiply. 1.2x equals 6.6. Divide both sides by 1.2. 6.6 divided by 1.2, if you put it in your calculator, you will get 5.5 meters. So now you've used similar triangles in order to help you find the height of that stone. The nice thing about this is you can use that to find any height, the height of your school, the height of the Eiffel Tower. It's a very convenient way to find the height. Let's look at one more example. In this example, we're going to look at a little bit of a different technique. Here we want to find the height of this canyon or this wall, and we have a person standing here who's 5'5". Now, what we have in the middle right here is a mirror. So what's happening is that this person is looking into the mirror and creating this angle, and then from the mirror is looking up at the top of this wall, and that creates the same angle. So the reflection of his view to the mirror and then back up is the same angle. And so in both of these cases, we have a small triangle and a large triangle. We again have similar triangles due to angle. We have two right angles that are obviously the same measure, and then we have these two angles caused by the reflection into the mirror, and so those angles are similar, or congruent, I should say. So our triangles are similar. That means our sides are all proportional. So we can set up the same type of proportion that we just did. We can take 6 feet, which is the distance from the man to the mirror, and compare it to 34 feet, which is the distance from the mirror to the canyon wall. And there's our ratio, or our proportion, that we're going to set equal to the height of the man over x, the height of the canyon wall. Now, just by cross multiplying, and we can take in our calculator 34 times 5.5 and get 187. Divide both sides by 6, and we get 31.17 feet. And that's the height of the canyon. So we were able to calculate that without actually having to climb to the top of the canyon, drop a tape measure down, which would be very problematic. This concludes our lesson today on indirect measurement. And now you can see how we can use this indirect measurement to help us solve for missing measures in similar triangles.